No, you can open the door.
Oh, I was like,
Okay.
Like in a Titanic.
Break is over. Let's talk about this stuff some more. So I started out, let's see if I'm going to be over here. I should move the microphone. I started out this little talk about capacitors by talking about parallel plates in a vacuum, which would be, the simplest case from the point of view of dealing with it mathematically. But as a practical matter, it's good to have some sort of an insulating material between the plates for a couple of reasons. One of which is you can get the plates a lot closer together without worrying about them touching each other. And for another thing, the presence, all else being equal, the presence of that insulating material increases the capacitance of the capacitor. And here's how that works. The terminology here is the substance that's placed between the plates is called a dielectric, okay? That just simply means some insulating material that your electric field exists in. So let's say, let's make a copy of it with a battery where I can point at stuff as I'm talking. So here's your parallel plates. And there's the battery. That's the negative terminal and that's the positive terminal. And so you put your two pieces of metal parallel to each other, and when you hook it to the battery, like I already said earlier, a bunch of these electrons can get away from the other electrons by going over here. Like charges repel. And an equal number of electrons gets pulled into the positive terminal of the battery. And actually attraction to the attraction of the minuses to the plus plate is also a factor in making some electrons leave the battery and come over here. But in a fraction of a second, you reach an equilibrium where the capacitor is fully charged. So far, there's just empty space between the plates. Now you come along and you slide a piece of plastic or glass or some insulating substance like that in between there. That insulator becomes polarized. Just like the other day in the lab when I had you come over here near the faucet and you held the charged rod next to the water and the water kind of swooped to the side because one side of the water got positively charged and the other side of it got negatively charged. Well, in general, whether it's water or glass or anything else, you put a material in an electric field and if you had what was originally a nice symmetrical atom where the electrons are just orbiting around in a nice even orbit, you create an electric field that's pushing on those electrons as they try to orbit, and they're going to start spending more time on one side of the nucleus and less time on the other side of the nucleus. And so even if the atom was not originally, if it didn't originally have a plus and minus side, which some molecules naturally do, but even if it doesn't, it's going to develop one in an electric field, and they're all going to be lined up with the positive sides on the bottom and the negative sides on the top. So that's how some material like glass, where charge is not free to move around, becomes polarized. It's down at the atomic level. You've got a whole bunch of, well, maybe I should say the molecular level, but you've got a whole bunch of molecules that become like this. Of course, there's more than 8 molecules in it, but you get the idea that the top surface of it's going to be negative and the bottom surface of it's going to be positive. So after you've inserted this dielectric, okay, there was some electron sitting out here in the middle of the wire, and previously it was just as strongly repelled by the negative terminal of the battery as it was by these electrons over here in the capacitor. Well, then you introduce this additional layer of positive charge right next to the negative plate here. Well, our electron here that can't make up its mind which way it wants to go, that's the deciding factor. It's attracted to the negative, to the positive side of that dielectric, and it and a lot of its buddies come on over into the capacitor. Of course, you know, it's also repelled by the negative side, but that's much further away, so that doesn't matter as much. And so this polarized piece of insulating material upsets the balance, makes more charge flow in, and that increases the capacitance of the capacitor. The factor by which it goes up is the dielectric constant is a property of the material. Okay, if the material you've put in here is this stuff, the capacitance goes up by a factor of 2. But if what you put in there was that other stuff, then the capacitance goes up by a factor of 3 because it becomes more strongly polarized than the first thing did. And so the ratio by which you increase the capacitance is one way of defining the dielectric constant anyhow. Just plain C with no subscript is the capacitance you've got with the dielectric present. C without any subscript, or C with the 0 subscript, sorry, that's the capacitance when there's nothing in there. So in the previous example, you calculated the capacitance of that device up there with nothing between the plates. I'll just go ahead and write this out. This is just a quick little one-liner kind of thing. Just, well, everybody do this much. Polystyrene. There is a table in your formula sheet. I could look up the page number, but it's page 6, okay. So you go in there and you look up the dielectric constant for polystyrene, and it comes out 2.56. Everybody see where I'm getting that from? Okay, so capacitance equals kappa. The symbol here is the Greek letter kappa. Times the capacitance with nothing. And so we've got 2.56 formula sheet. Times what the capacitance would be with nothing between the plates, which was the answer to number 5. And then problem number 7 is basically just the same stuff you've just done all over again. I'll just write that out and move along. So we got a really, well, physically large capacitor in terms of its dimensions, a meter square. It's not a very big capacitor at all in terms of its capacitance, but again, That's because the plates are so far apart. We're supposed to, first of all, find its capacitance. So if there was nothing between them. See, part A is actually a two-step thing. It's going to be kind of like part A of number 5 together with number 6. You've got this capacitor that's full of paper, or if it's 2 millimeters thick, you might want to call it cardboard, whatever. The term that's in the formula sheet is paper, so let's call it paper. So you've got this heavy paper, and the capacitance is going to be the dielectric constant times what the capacitance would be if the paper wasn't there. So you have to put those two things together. If there's nothing in there, so you throw the numbers at it, and 1 meter times 1 meter, pretty easy to figure out the area of that, 1 square meter. 0.002 for the separation of a meter. 4.43 10 to the negative 9 farads. But that's not what it asked for yet. Because you don't just have nothing between the plates, you've got that paper in there. So you look up the dielectric constant, 3.7. For paper. And I can probably squeeze the answer over here in the corner. 1.64 times 10 to the negative 8 of a farad. Or kind of like I did with the other one when I wrote up the answers on the notes there. I didn't feel like fooling around with scientific notation. This would be equivalent to 0.0164 times 10 to the negative 6 farads, which is to say 0.0164 microfarads. And then part B, how much charge, this amount of charge, the 0.197 microcoulombs, that's going to be the answer here. That's the charge on each plate. I mean, if you add the two plates together, it adds up to 0 because they're always equal and opposite. One plate is positive 0.197, the other plate is negative 0.197. So the Q here in this calculation stands for the charge on each individual plate. Part B. If C is equal to Q over V, and it's not terribly significant really if I'm using a capital Q or a lowercase q. I may not be entirely consistent about that all the time, but Q is equal to C times V, or C times delta V maybe is the more precise terminology for, or symbol for it, delta V being the potential difference between the plates. I guess I'm being a little sloppy here. Anyhow, C is the answer to part A. The 1.64 and the -8. And it says you're applying 12 volts, 0.97 to the -7th coulomb. Now you might have noticed that that table where you looked up the dielectric constant, where the 3.7 or the 2.56 comes from, it's got another column that says dielectric strength. That is related to a phenomenon called dielectric breakdown. I think I already explained the difference between conductors and insulators. Or was that in my other course? Anyhow, you're probably aware that things like rubber don't conduct electricity and things like metal do conduct electricity. Well, you know, that's assuming moderate voltages. You can get an electric current to pass through anything if you crank up the voltage high enough. Million volts, you'll get a current to flow through it. Glass, anything, doesn't matter. Unless it's a really thick piece of glass, and then maybe you need 10 million volts. But, you know, air is an insulator, and there's this stuff called lightning. Anyhow, yeah. So, good conductors of electricity contain lots of electrically charged particles that are free to move around. Because an electric current is a flow of charge, there has to be charges that are free to move. Like the free electrons that you have in a metal, or like the ions floating around in a salt solution or an acid. The salt solutions and acids are also very good conductors of electricity. Well, you know, a substance like glass or rubber, well, you know, everything's made up of atoms that are full of electric charges, but in a substance like glass, they're not free to move around like they are in a metal. But if you apply a strong enough electric field, it'll rip the electrons out of the molecules, okay? And then once they're ripped out, now they're free to move, and there's your discharge, your spark. So how strong of an electric field it takes to do this is a property of the material. And this property is called dielectric strength. That's the other column of that table. So, for example, a number of years ago, we were on vacation and we visited White Sands, New Mexico. It turns out in the desert, the humidity is really, really low. There's this national park there, and they've got this kind of walkway, this sort of boardwalk kind of thing built where you can walk back in and admire all the nice sand dunes and the desert vegetation that grows around them and all that. But they didn't make it out of actual boards. It was this plastic stuff that I think is recycled milk jugs or something like that. And there was this railing running along the side. And there were the upright things that support the railing were aluminum, and there was an aluminum bar that went along underneath this plastic railing. And I'm walking along, starting to go back in there, and I'm pretty quickly noticed that as my hand goes along the railing, it's like snap, snap, snap. The sparks kept jumping off my fingers to that piece of metal that was right under the railing. So of course I took my hand off the railing pretty quick. But then, you know, after that, every time I'd brush against my wife, she'd be like, stop that. And it was probably like 10 or 20% humidity, you know. So I don't know if I was throwing sparks a whole centimeter long, maybe not. Just seemed that way. But if I was, well, to make the math easier, let's simplify me and my wife into a set of parallel plates. And if a spark jumped a centimeter to get from the one of us to the other, what does that make the potential difference between us? Well, you know, parallel plates, this will at least give us a crude estimate, even if it won't be accurate right down to the tenth of a volt or anything, but I guess I had it in mind that you would calculate this. So go ahead, look up the dielectric strength of air, because that's what the spark is jumping through. And then the dielectric strength is E, the electric field. Hopefully you remember from earlier today that E is volts divided by meters, delta V over D. D would be the centimeter. Okay, this one's a pretty short, quick one actually. So yeah, the camera's still over here. If E equals delta V over D, that rearranges into delta V equals E times D. Volts per meter times meters gives you volts. The figure given on the formula sheet is the for the dielectric strength of air. Maybe I should label it. Somebody was looking at this later. If any of you ever becomes a teacher, my rule of thumb anyhow is I kind of assume that at any given moment, maybe 30 to 50% of the students are actually listening to me. So anything that's important, I should probably write down so that when they get back to it, it's there. So you go into that table and you look up the dielectric strength of air. For a realistic problem, it's probably not exactly that. This is probably for dry air, as in 0% humidity. And so if you're talking about, you know, scuffing your feet on the carpet down here in the library, well, that'll be the right order of magnitude anyhow, but it might not be exact. Volts per meter times meters gives you volts, 30,000 of them. Now, I don't know. My wife and I maybe were closer than that when sparks would jump off of me onto her because I was charging myself up, rubbing my hand on that railing. But even if it was only a third of a centimeter, you know, just a little over 3 millimeters. I mean, everybody has scuffed their feet around on a carpet and had a spark that long jump off their finger probably. That would still be 10,000 volts. So then that might lead to the question of, why do you hear all the time about people getting electrocuted off of 120 volt house current, but you can go scuffing your feet around on a carpet and get 5 or 10,000 volts on your body, and aside from the minor tingle, it doesn't really hurt you any? Well, The place where I've got that written in the notes is a couple of weeks in the future, but the short version of the story is just that it's the amps that hurts you, not the volts. High voltages tend to be dangerous because they can push more current through you. But not in the case of just putting a static charge on yourself. You scuff your feet around on a carpet on a dry day, you put a small amount of charge on your body. Each of those few electrons has a lot of energy. That's why the voltage is so high, but there aren't very many of them. And so there's just a small amount of current that lasts for just a tiny fraction of a second. And if 10,000 volts was maintained across your body for any significant amount of time, like if you got messed up with, some electrical wires, high voltage wires, yeah, I wouldn't want to have to be the person who notified your next of kin. But, for just a static charge, it's harmless. So the last thing I put at the bottom of this page is just some of the symbols that are used when you draw a picture of a circuit, which is something we're going to do from time to time. I mean, a little earlier I drew a battery and I made a box and wrote battery on it. Put a plus and a minus sign. If you've ever looked at an electrical schematic, that's not what people usually do. The symbol for a capacitor is a little picture of some parallel plates. A battery is this symbol here. Which looks like it might actually show up. The long side of the battery symbol is the positive terminal. The short side is the negative terminal. Normally, you don't see it written with a plus and minus sign next to it like that, but on your formula sheet, it is written with a plus and minus sign next to it, just like that. So if you need to, you can look up which side is positive. But I always just remember it kind of like this. Positive is the higher voltage side. I think I already mentioned that earlier today. Positive is a higher potential, negative is a lower potential. The bigger side of the symbol is where you have the bigger voltage. And if you just keep that in mind, that might be helpful. A resistor, like an incandescent light bulb, for example, would be a resistor. Little squiggly line there. A switch kind of looks like a picture of a switch. You just push down the little thing and it makes contact. You lift it up and it loses contact. And so, having gone over how to draw pictures of this stuff, let's talk about combinations of capacitors. So, an old trick, of course, nobody does this anymore because nobody repairs electronic devices anymore because they've gotten so cheap you just throw it away and buy another one. But actually, that's not entirely true. There's still, $50,000 pieces of medical equipment and things like that. But, well, let's say it's 1951 and you're going to repair somebody's radio for them, back in the days when people still did such things. So you figure out there's a bad capacitor in there. In 1951, you might have still been calling it a condenser. If you ever come across that, it's an old-fashioned term for a capacitor. I need a 10 microfarad capacitor. And you look in the drawer, oh, I'm fresh out of 10s. But I got lots of 5s. I don't feel like hopping in the car and driving down to the store to buy one lousy capacitor to fix this thing with. If you take 2 5s and you put them together the right way, it's equivalent to a 10. So you can stick them in there and it'll work just fine. And so whether 2 5s are equivalent to a 10 though, depends on whether you hook them up in parallel or whether you hook them up in series. So a series circuit Well, maybe the most familiar example of that kind of thing, at the moment we're talking about capacitors, we'll get to resistors, I think that's next week. Light bulbs are resistors, but most Christmas tree lights are in series. You know, the annoying kind of Christmas tree lights where when one of them burns out, the whole string goes out. Electric current flows out of, well, here I've drawn it as a battery. Christmas tree lights are usually house current, of course. First, it would go through the one light bulb, then it goes through the next light bulb, and so on and so on. That's a series circuit. The various devices in your house are hooked up in parallel, okay? If I gave each of you a lamp and told you to plug it in there on your, the outlets under the counter, if I don't know if all these are on the same circuit or if it's a couple of different circuits, but for the moment, if there's a panel down the hall here with a breaker box, and if all of these desks were on the same circuit, then if a whole bunch of electrons flows out of here, well, some of the electrons go through the lamp on that table. Some of the electrons go through the lamp on that table. Some of them go through the lamp on that table, and so on. Each lamp gets the full 120 volts when it's a parallel circuit. Probably I should have this thing aimed over to the side again like I did before. So, assuming no voltage loss along the wires, which would be actually completely true if it was a bunch of capacitors because there's no current flowing, then, if this side of the battery is, say, 12 volts higher than this side, each of these plates on the top here are at the same potential as this terminal of the battery. Likewise, this terminal of the battery is connected directly to each of the plates on the bottom. So if you've got 12 volts across the battery, you've got 12 volts across each of the capacitors. So delta V is the same across each one. The total charge on the group, well, if a whole bunch of electrons flow out of this battery when you first hook it up, some of those electrons will come around here and end up on that capacitor. Some of them will come here and end up on that one, and so on and so on. The total amount of charge that flowed out of the battery ends up with some of it being here, some of it being here, some of it being here. Q total equals Q1 plus Q2 plus Q3. Take that equation, divide it through by delta V, the voltage that's across all of these capacitors. That's what I've got written here. And then remember the definition of capacitance. Q over V, charge stored per volt, that's equal to C. So the equivalent capacitance of the entire group, in other words, what one capacitor would be equivalent to having this whole group of capacitors, is equal to C1 plus C2 plus so forth. So if you need a 10 and you got a drawer full of 5s, you want to hook them up in parallel. That's what, in other words, take your two capacitors and twist both sets of wires. You got a wire coming out of each end of the thing. Twist together the wires coming out of the one end of both, and twist the wires coming out of the other end of both, so that it's hooked up like C1 and C2 here. And then 2 5s will give you a 10. On the other hand, if you hook them up in series, well, this time it's the charge that's the same on each capacitor, because if everything starts out uncharged and then you hook it up to the battery, a bunch of electrons come out of the negative side of the battery, and they end up on the all of them end up on the negative side of the first capacitor they get to. Well, every time an electron goes in one side, an electron has to leave the other side. The plus and minus plates always have equal and opposite charges. The electrons are moved, when you hook it up to the battery, it creates an electric field inside the wires. And that electric field pushes the electrons that way. So a bunch of electrons leave this capacitor. Where do they end up? They end up on the negative side of this one. Same number of electrons that were put on the negative side of this one. And a bunch of electrons leave the positive plate here and end up on there, and so on for however many capacitors there are. So the total amount of charge that flows out of the battery is equal to the charge on each individual capacitor. Q1 equals Q2 equals Q3. We'll just call it Q. The total voltage gets split between, like, if you've got 120 volts and you've got 60 light bulbs on your string of Christmas tree lights, each bulb only gets 2 volts, okay? It kind of comes down in steps. If this is at plus 120, then you've got 118 there, 116 there, 114 there, and so on down the whole string of lights. Q total is equal to, or V total is equal to the voltage across, whether it's capacitors or whether it's resistors, V1 plus V2 and so on. Take that, divide through by Q, which is the same on all of them. And then again, remember the definition of capacitance. C is equal to Q over V. That would mean V over Q is the reciprocal of the capacitance. 1 over C equivalent is equal to 1 over C1 plus, etc. If you take a pair of 5s and you hook them up in series, that's equivalent to 2.5 microfarads. That's how it works out with the formula. I tried to put some helpful comments next because, you put a problem on a test and people look at things that are hooked up a certain way and they think they're in series, but they're not in series. Or they think they're in parallel, but they aren't really in parallel. So things to look for. There are no junctions between things in series, like right over here, where this wire connects in between C2 and C3, or where this other wire connects between C1 and C2. That's called a junction. Same terminology you have with railroad tracks, where this track hooks in with the other one. And so in the first picture, yes, these are in series. But over here, where you've got other branches going off in between, those are not in series. Whether you're talking about capacitors or resistors or anything else, if they're in parallel, both ends connect together, like I showed in this picture. Both ends, well, I guess when I used the word both, I must have been thinking of 2 capacitors. Well, no. It was okay. The left ones are all hooked together, and the right ones are all hooked together. So yeah, both. The left side and the right side, they're both all hooked up. And similar looking picture where they're not in parallel. Yeah, on the left-hand side, they're all hooked together, but not on the right-hand side, not before you have to go through some other stuff. So let me run through example number 9, and then you'll do example number 10. And then after that, I think we can get probably 20 minutes or half an hour into section 3 also. Like I probably said the first day, I'm gonna, on the days of the lecture classes anyhow, I'm gonna usually try and take you right down to 5:25 because I'm getting myself all prepped up for next year when we run a 15-week semester. So I want to see how much I can compress the course. If it doesn't work, I'll have to figure out how to compress it even more somehow. But I think I can make it fit without changing too much. So number 9. Well, this isn't just a bunch of capacitors in series, and it's not just a bunch of capacitors in parallel. It's I guess you'd call it a series parallel combination. So you're not going to get the answer in just one step. You have to go through a couple of steps. And in fact, I think I put one in the homework where it's like 3 steps before you get to the answer, if I remember right. So the first thing to notice is that even though all 4 of those capacitors are not in series with each other, the 3 across the top are. Okay, so let's just get back to that 13 microfarads on the bottom. For a moment, let's just consider this part of the group. We've got 20, 30, 60. Okay, no junctions in between anything there. Those 3 are in series. So what one capacitor would be equivalent to those 3? Well, they're in series, so here's the equation that goes with that. I'll call its equivalent resistance CS, S as in the series part of the group. Seems like a good name. Convert microfarads to farads if you want to, but it's not really necessary. Whatever unit you put in will be the unit you get out. So probably convenient just to leave it all in microfarads. Well, textbook problems like this are usually rigged up so there's a convenient choice for the common denominator. So that's how I'm going to work my way through the math. You get out and you just grab a bunch of capacitors and start hooking them up, and they tend to have numbers like 117 and 41 and not quite such nice common denominators. In that case, you might want to just work with the numbers in decimal form instead. But if you do that, beware of round off errors. Okay, the nice thing about fractions is they're exact. Decimals are fine as long as you don't, like 1 over 30, 0.03333333. If you round that off to 0.03, you just changed it by 10%. So your calculator can handle like 8 or 10 digits at least. Just throw stuff in the memory, or at least don't round it off too much. Our common denominator here is going to be 60, so we've got 3 over 60 plus 2 over 60 plus 1 over 60. Which adds up to 6 over 60, better known as 1/10. And then where some people get caught sometimes is they get to here and they say, okay, so the 3 of them together are 1/10 of a microfarad. That's 1 over C. Don't forget to take the reciprocal. If 1 over C is 1 over 10, it's 10 microfarads. So, maybe I'll make a little more space to write. So the actual capacitors, the 4 actual capacitors that you've really got, are equivalent to having these 2 capacitors arranged like this, because I just got done figuring out that this group of 3 would be equivalent to a single capacitor of 10 microfarads. And that group of 3 is in parallel with the 13. Capacitors in parallel, just add. So number 10, here's another series parallel combination. See what kind of luck you have with that. Number 10. So once again, look at just part of the circuit, and these 2 over here, the 6 and the 10, by themselves, that's parallel. So let's simplify down that part of it first. That group of 2 is equivalent to having a single capacitor of 16 microfarads. So since the pair on the right is equivalent to 16, the actual capacitors are equivalent to having an 8 and a 16 in series with each other. So the equivalent capacitance of the entire group is 1 over 8 plus 1 over 16. Once again, nicely rigged up to have a common denominator. So 1 over C is 3 over 16. That means the equivalent capacitance is 16 thirds, which I suppose you could leave the answer like that. That's what they kind of like you to do in a math class. Or if you move in circles where decimals are more the way people tend to do things, about 5.33. Okay, so first 20 minutes or so of section 3. And for anybody who has to leave early, well, you know, that's kind of what that camera's there for. So I guess I actually said this earlier today, the difference between conductors and insulators. A conductor is any material that contains lots of free charges. Salt water is full of ions. Whatever it is, you establish an electric field in it, maybe by hooking it up to a battery. Any charged particles in the substance get pushed on by that electric field. If they are free to move, they flow, and a flow of charge is a current. If it's a substance like glass, where all the charged particles are tightly bound in place, they don't flow, and that makes them, unless you apply a really high voltage, and that makes them an insulator. More terminology, an electric current is a flow of charge. Any kind of a flow of charge. Example I always like to give is, one more time, you remember this thing here at the first day? If I had a whole bunch of these rods and I charged them up with my piece of fur here, and I passed them out to a whole bunch of people, and then I told them to line up and run down the hall with them, that is an electric current. It would be a very small electric current, probably something maybe even less than a microamp, but it doesn't necessarily have to be electrons. Any kind of flow of charge, whether it's ions, whether it's a flow of charged plastic rods, any sort of flow of charge is an electric current. So, electric field, I've drawn a picture here where I've got looks like a big fat wire, hopefully something with a lot of resistance, is hooked up to a battery. When you connect this wire to the battery creates an electric field inside of the wire. Any free charges inside the wire flow. You may notice I've indicated these free charges by little circles with plus signs on them. An electric current is conventionally thought of as a flow of positive charge. I guess it says that further down the page somewhere. But, you know, sometimes people kind of hesitate and go, wait a minute, you know, if I plug in my toaster, I know it's a bunch of electrons flowing through there and they're negative. Well, yes, the charge carrying particles are negative in the case of a metal. But first of all, there are other types of conductors where the charge carrying particles are positive. If you dissolve salt in water, it becomes a good conductor. If you create a current in that, half of the current is sodium ions going one way and half of the current is chlorine ions going the other way. So half positive, half negative in that case. In certain types of semiconductors, effectively all of the current is positively charged particles, so-called P-type silicon or germanium or some substance like that. Or if you want to get into biomedical applications, let's say I decide to wiggle my finger. Well, what happens is that what amounts to a small electrical impulse travels down the nerve fibers. Those of you who've taken any biology know that how that works is you've got sodium and potassium ions diffusing from one neuron into the next. Those are positive ions. That little electrical pulse is a flow of positively charged particles, not negative ones. So yeah, in some things, the current is actually a flow of negatively charged particles, but in other things, it is positively charged particles. And aside from that, it doesn't matter anyhow. Whether you've got plus things going the one way or minus things going the other way, well, like if it's a capacitor and you run a wire from one side to the other, whether you've got minuses headed toward the plus side or whether you've got pluses headed toward the minus sign, the capacitor still discharges either way. The pluses and the minuses get together and cancel each other out. So there are very few observable differences between having plus charges going one way and negative charges going the other. The only difference I'm aware of is something called the Hall effect. You can actually see whether it's positive or negative charges with the Hall effect. But otherwise, you know, it's kind of like on a day like today, if you open up the door to your house, does heat go out or does cold come in? Well, yeah, technically there's a right and a wrong answer to that, but for most purposes, it doesn't really matter, you know. It gets colder in your house either way. And that's kind of the situation here. So all of this stuff was set up many, many, many years before the discovery of the electron. Everything was defined in terms of positive charges. And when the electron was discovered a little over 100 years ago, there really wasn't any good reason to throw away all the books and write new ones and make everybody get used to doing things the other way around. So, anyhow, electric currents flow a charge, an electric field in a conductor pushes on the free charge, makes a flow, blah, 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 said all that. The electric current, I, this is the rate of flow, okay? It's like if you're standing on a bridge looking down into a creek. In the springtime, when all the snow is melting, maybe you've got 20 gallons per second flowing past you under that bridge. And later on in August, when everything's drying up and everybody's grass is dying and all that, maybe now there's only 2 gallons per second flowing under that bridge, okay? Gallons per second of flowing water, coulombs per second of flowing charge, same idea. It's telling you the rate of flow. Is there a lot of water going down the creek or is there only a little bit of water going down the creek? So coulombs per second going through that wire. Another combination of units given a name of its own. This one's called an ampere, which a lot of people just kind of nickname it an amp for short, but unlike a volt and a farad, it hasn't been officially shortened from the guy's name. So, yeah, a long line of people has a glass rod, 1 microcoulomb of each. 2 of them pass you each second, find the current. Current, charge per unit time, coulombs per second. You divide it out, you've got 2 millionths of an amp, 2 microamps. Yeah. The glass rods, when you rub them with silk, they are actually positively charged. Those Bakelite rods, the black ones, you rub them with the fur, they're negatively charged. And in that case, the direction of the current would be opposite of the direction that the people are running, for the reason that I just gave that whole long speech about, with it being thought of as a flow of positive charge. So why don't you try a couple of short problems here? Number 1 and number 2. Number 1. Current is charge per unit time. Coulombs per second, the rate that the charge is flowing. Q is the thing the question asks for. It says how much charge passes one particular point. So we've been using Q for charge all along. This rearranges into Q equals I times T. Current is 4.1 amps. And then here is where some people get caught sometimes because they're not thinking carefully about what unit things are measured in. An amp is a coulomb per second. Coulombs per second times minutes doesn't give you coulombs. You have to convert minutes into seconds. 492. I suppose it's a little easier to remember that when the answer is written right underneath the question, and you're obviously not going to get 8.1, but when it's like a test question or something where you don't have the answer looking at you, people tend to get caught by that. Number 2. Find the current. Gives you the number of electrons that pass some particular point, as if you could see them and count really fast as they go by. Current is I, so this time the question is asking for I. Current, or as it's sometimes kind of nicknamed, the amperage, because it's measured in amps. Q is the total amount of charge. Well, you're not told the amount of charge, you're told the number of electrons, but you can look up how much charge is on each electron. So the charge on one electron times the number of electrons would be the total amount of charge that goes by. 1 times 10 to the 21st electrons times 1.602 times 10 to the negative 19th. I guess you could label that as being coulombs per electron. Coulombs per electron times electrons gives you the total number of coulombs. Time is 30 seconds. So electrons times coulombs per electron gives you 160.2 coulombs divided by 30 seconds, 5.34. And again, a coulomb per second is better known as an amp. And so when we start up the next class a week from now, the stuff between problem number 2 and the next few things it says there is stuff I've already mentioned, like about how electrons being negative flow in the opposite direction of the conventional positive current. And we'll start out at the heading that says electrical resistance.